Right now, the physical space you are occupying, like the empty air in your office or your car or your living room, it's not empty at all.
No, not even close. It's completely saturated.
Yeah, it's vibrating. You are sitting inside this densely packed, really tightly regulated matrix of invisible electromagnetic pulses. I mean, before you even finished your first cup of coffee this morning, you interacted with dozens of these distinct silent frequencies.
And, because human eyes can't perceive the radio spectrum, we tend to treat wireless connectivity as this simple binary. It's either working or it's broken.
Right, exactly. We rarely look under the hood at the actual physics of the waves.
Well, we treat it like utility plumbing. You turn the tap, water comes out, and you just don't think about the municipal pipe system.
Yeah.
But wireless networking isn't just a utility. It is a highly volatile, shared physical medium.
Which is wild to think about.
It really is. The moment you transmit a signal, you are physically changing the electromagnetic environment of everyone around you. So understanding how those signals are structured, how they negotiate space, and why they degrade is just fundamental to navigating modern infrastructure.
And that is exactly the foundation of our deep dive today. We are looking at a highly technical set of notes from Professor Messer's IT certification training courses. Specifically, the CompTIA plus 220-1201 section on wireless network technologies.
It's a great resource.
It really is. So our mission here is to map out this invisible architecture for you. We want to decode the acronyms, absolutely, but more importantly, we want to understand the physical mechanisms at play.
Right, like how your devices actually manipulate energy to push data through solid walls.
Exactly. And why understanding that architecture fundamentally changes how you view the devices you use every single day.
Now, the certification material obviously approaches this from the perspective of an IT professional troubleshooting a network, but the underlying concepts are universally applicable.
Oh, for sure.
If you understand the physics outlined in these notes, a dropped connection stops being this frustrating mystery and becomes a highly predictable consequence of environmental factors or just frequency congestion.
Okay, let's unpack this, because before we can look at how data actually modulates onto a radio wave, we have to establish who dictates the rules of the road, right? Who structures those waves.
Right, the governing body.
Yeah, and the source material points us immediately to the IEE, the Institute of Electrical and Electronics Engineers, and specifically their 802.1 committee.
The famous 802.11.
Right, and for decades, consumer networking hardware was defined strictly by the literal committee amendments, 802.11a, B, G, and, well, sorry, not ... but you get the idea.
Right, those designations represent major evolutions in the physical layer of wireless transmission. Every time the committee approved a new method for encoding data or utilizing radio spectrum more efficiently, they just appended a new letter or a pair of letters to the 802.1 standard.
Which is, okay, technically precise, but from a consumer standpoint, relying on an appended letter string to indicate technological generation is a disaster. Engineers are terrible at marketing.
They really, really are.
If you walk into a store, you shouldn't have to parse whether 802.1 NSE is vastly superior to 802.11n. It's like trying to sell a car using only its VIN number.
It demands that the end user basically memorize the committee's chronological workflow, which makes no sense for the average person buying a router.
Exactly.
But, the industry did recognize that friction. The source details this massive shift toward a user-friendly generational naming convention that actually aligns with how consumers purchase electronics.
Thank goodness.
Yeah. So the 802.1 SE standard was retroactively branded as Wi-Fi 5, and then the subsequent 802.1 AX standard, which introduced significantly more efficient channel allocation, that became Wi-Fi 6.
Right, and there's the 6E version too, right?
Yeah, Wi-Fi 6E is an important extension of that. And then the most recent standard covered here, 802.1 BB, is just marketed as Wi-Fi 7.
Which is just so much easier. It strips away all the engineering nomenclature on the box. You still have the 802.11 specifications operating under the hood, obviously.
Sure, your hardware is still physically processing the AX or B protocols.
Right, but the Wi-Fi 5, 6, and 7 branding allows you to instantly identify the generational capability of the hardware.
It creates a baseline of understanding. When you see Wi-Fi 7, you immediately know you're accessing the most current modulation schemes and frequency utilizations without, needing an engineering degree to read the IE white papers.
So what does this all mean when we get into the actual signals? Let's get into that frequency utilization, because this is where the physics get incredibly relevant to our daily lives.
This is the fun part.
Yeah. The notes highlight 3 distinct frequency ranges that these 802.11 standards operate within. 2.4 gigahertz, 5 gigahertz, and 6 gigahertz. And when we say a router is broadcasting at 2.4 gigahertz, we're talking about the physical oscillation of the radio wave, which is 2.4 billion cycles per second. But a device doesn't just broadly scream into the 2.4 gigahertz void. The protocol divides that spectrum up.
Yeah, the standard organizes the spectrum into channels. It's a lot like a TV station preset or a radio dial.
Because having to memorize a frequency like 2.437 gigahertz to connect would be absurd.
Completely. And what's fascinating here is how the notes provide the specific translations for those channels. When your router interface indicates you are transmitting on channel 6 in the 2.4 gigahertz band, the physical reality is that your hardware is centering its transmission exactly at 2.437 gigahertz.
Okay.
And if you switch to the 5 gigahertz band and select channel 44, your device begins modulating data at a center frequency of 5.220 gigahertz.
I want to look closely at that term center frequency because that implies the channel isn't just a single microscopic point on a dial, right? It's a spread.
Yes.
And the notes bring up the concept of bandwidth, specifically 20, 40, 80, and 160 megahertz channel widths.
Right, because bandwidth is the literal physical width of the radio spectrum you are consuming. So if you center your transmission at 2.437 gigahertz, but you're using a 20 megahertz bandwidth, your signal spreads 10 megahertz above and 10 megahertz below that center point.
Okay, I see.
You are physically occupying that entire chunk of the spectrum to push your data. And wider bandwidths allow for vastly higher data throughput. I mean, a 160 megahertz channel can carry an immense amount of data compared to a 20 megahertz channel.
But expanding that channel width comes with severe physical constraints, right? Especially in the 2.4 gigahertz band. I mean, this seems to be the root cause of basically all our chronic wireless issues.
It absolutely is.
Because the 2.4 gigahertz spectrum is so heavily utilized. Lower frequencies have longer wavelengths, so they're much better at punching through physical obstacles like walls and furniture. But, and this is the crazy part, the entire usable 2.4 gigahertz band is roughly only 80 megahertz wide in total.
Yeah, that physical constraint dictates the entire topology of 2.4 gigahertz networking. If the total available spectrum is only about 80 megahertz wide and a standard Wi-Fi channel requires 20 megahertz of width, well, basic division tells you the reality.
Right.
You can only fit 3 independent 20 megahertz channels side by side without their edges bleeding into each other. Channels 1, 6, and 11.
Wow. So if I live in a dense apartment building and there are, say, 20 different routers broadcasting a 2.4 gigahertz signal, they are entirely confined to just those 3 non-overlapping channels.
Yep, they have nowhere else to go.
So when my router is on channel 6 and the 3 apartments next to me are also on channel 6, our 20 megahertz transmissions are literally physically colliding in the air.
In networking terms, that's called co-channel interference. Your devices essentially have to wait their turn to speak.
Because it's basically a traffic jam.
Exactly. The physical medium, that specific 20 megahertz slice, is already saturated with energy. The noise floor rises so high that your laptop literally cannot distinguish your router's signal from the neighbor's signal.
That perfectly illustrates why the industry had to open up the 5 gigahertz and 6 gigahertz bands. It wasn't just about speed, it was about sheer physical volume.
Yeah.
We needed massive new superhighways.
The jump to 5 gigahertz fundamentally changes the math. Because there is so much more available spectrum, you don't just avoid overlapping with your neighbors. You also have the physical room to bond channels together.
Oh, right, making them wider.
Yeah, instead of being restricted to a 20 megahertz slice, you can configure an 80 megahertz or even a 160 megahertz channel width. You're utilizing a massive swath of contiguous spectrum to move data at gigabit speeds.
And then the 6 gigahertz band, which was introduced with Wi-Fi 6E and expanded in Wi-Fi 7, pushes that even further. It opens up entirely pristine spectrum, allowing multiple ultra-wide 160 megahertz channels to operate simultaneously.
Without any overlapping legacy devices getting in the way, yeah.
But there's a trade-off, right? The wavelength. As we push into 5 and 6 gigahertz, the wavelength gets shorter.
Right, the attenuation is much higher. Shorter wavelengths carry more data, but they struggle to penetrate dense materials. So a 6 gigahertz signal that delivers astonishing speeds in the same room as the router will drop off significantly faster than a 2.4 gigahertz signal the moment you put a couple of drywall barriers or a concrete floor in the way.
So 802.11 Wi-Fi networks scale their frequencies to push massive throughput across buildings. But that broad coverage model isn't necessary for everything, right? Like when we look at personal peripherals, Wireless mice, keyboards, earbuds. We're moving from building-wide signals to personal-sized bubbles.
Right, moving from local area networks down to personal area networks.
And this is where the notes transition to Bluetooth.
Bluetooth operates on a completely different philosophy of connection. It's designed for continuous low-power pairing between adjacent devices.
But wait, the notes explicitly state that Bluetooth operates in the exact same 2.4 gigahertz range as older Wi-Fi.
That's right, it does.
And frankly, based on everything we just discussed about 2.4 gigahertz being a congested 80 megahertz wide bottleneck, where even 3 Wi-Fi routers cause a total traffic jam.
Oh,
How does that work?
it sounds like a recipe for a total signal collapse, right?
Yeah, if I'm working on my laptop and my Wi-Fi is pushing heavy data on 2.4 gigahertz and my Bluetooth mouse is sitting inches away using the exact same spectrum, why doesn't my mouse instantly jam my internet connection?
It's an excellent question, and it requires us to look at how different protocols treat the same physical space. See, the 2.4 gigahertz spectrum is designated as an ISM band, industrial, scientific, and medical.
Okay.
And the primary characteristic of an ISM band is that it's an unlicensed band, meaning anyone can build a device to use it without specialized government permits. That's why everything from baby monitors to microwaves to Wi-Fi routers use it.
So it's essentially a public commons for radio frequency, like the Wild West.
Exactly. But to prevent the tragedy of the commons, you need rules. Professor Messer's A-plus materials classify Bluetooth's method of coexistence primarily through the lens of power limitation.
Meaning they intentionally make it weak.
Exactly. For standard consumer devices, what we call Class 2 Bluetooth, the hardware is physically restricted to a very low power output. It limits its maximum range to only about 10 meters. The text points to this strict boundary as the reason Bluetooth establishes a localized network without destroying the broader neighborhood's Wi-Fi.
Okay, I understand the 10-meter boundary prevents my mouse from knocking out the router in the apartment next door, but it doesn't explain the physics of my desk. My mouse and my laptop's Wi-Fi antenna are literally millimeters apart. Power limitation doesn't solve point-blank interference, does it?
You're touching on a slight limitation of the specific A-plus curriculum notes we're reviewing. The certification material focuses heavily on range and power classification for IT deployment. But physically, to survive on that desk, Bluetooth doesn't sit still.
What do you mean?
Well, while standard Wi-Fi parks itself on a static 20 megahertz channel, say, Channel 6 Bluetooth uses spread spectrum frequency hopping. It divides the 2.4 gigahertz band into 79 tiny 1 megahertz channels, and it hops between them thousands of times per second.
Oh, wow. So it's rapidly dancing around the massive static block of Wi-Fi data.
It slips through the micro gaps in the spectrum. The low power output ensures the overall noise floor doesn't rise significantly, while the frequency hopping prevents the Bluetooth connection from being obliterated by the static high-power Wi-Fi transmission.
That is incredible.
It's an elegant solution to sharing an unlicensed band.
That mechanism completely changes how I view the devices on my desk. They aren't just broadcasting blindly, they are actively evading each other.
Exactly.
But whether we are talking about the static, wide channels of Wi-Fi or the rapid hopping of Bluetooth, both of these technologies rely on active powered transmitters, right? The router pulls current from the wall, the mouse pulls current from a battery.
Right, they generate their own power.
Here's where it gets really interesting. What happens when we need to communicate wirelessly with an object that has entirely zero power of its own?
This is where the engineering moves from signal processing to pure electromagnetic physics. The notes transition into RFID, or radio frequency identification. We interact with the RFID constantly, tapping a badge to unlock an office door, product tracking on assembly lines, or reading the microchip embedded under a pet's skin.
The physical architecture of an RFID tag is fascinating. The notes describe some as small as a grain of rice, while others are flat, laminated inside access cards. If you shine a bright light through one of those hotel key cards, you can actually see the internal structure.
Yeah, it's pretty neat to look at.
There is a very thin wire coiled around the entire perimeter of the card, and that wire connects to a microscopic chip in the center. But there is no battery cell. The
No.
chip is entirely dead.
It is entirely passive, and this requires a totally different understanding of radio waves. Up to now, we've talked about radio waves purely as carriers of data, but radio waves are fundamentally electromagnetic energy.
Right, it reminds me of the physics of a solar panel. A solar panel sits entirely dormant until a photon of light physically strikes it, at which point it harvests that energy to create an electrical current.
That's a great analogy.
An RFID tag seems to operate on the exact same principle, but instead of harvesting visible sunlight, It's harvesting the invisible radio frequencies emitted by the scanner to wake itself up.
That is precisely the mechanism, known as electromagnetic induction. When you bring that passive access card within a few inches of the card reader, the reader is actively pumping out an electromagnetic field,
Okay.
and that wire coil inside the plastic card acts as an inductor. When it passes through the scanner's field, the field physically induces a microscopic electrical current inside the wire.
So the scanner is literally powering the chip through the thin air.
Yes, the current travels from the coil to the microchip, providing just enough electrical voltage to wake the processor up. In that fraction of a second, the awakened chip takes its unique identification number and modulates it back through the coil. It alters the electromagnetic field in a way that the scanner can detect, a process called backscatter. The scanner reads the modulation, authenticates the ID number, and unlocks the door. And the moment you pull the card away from the field, the chip loses power and goes completely dormant again.
That's practically magic. Now, the notes do make a distinction that active RFID tags exist, which contains small internal batteries for longer-range scanning, like a transponder tag on your car windshield talking to a toll booth reader.
Right, those need to work at highway speeds from farther away.
But the passive, unpowered tags represent a profound leap in capability, and if we connect this to the bigger picture, it leads us directly to NFC, right?
Exactly. Near-field communication, or NFC, is the evolution of that passive induction. It operates on the exact same underlying physical principles as RFID, utilizing the 13.56 megahertz frequency to create an induction field.
But where an RFID tag is typically a one-way street, the tag harvests power, screams its ID number, and dies. NFC builds on that to facilitate complex two-way communication. This is the protocol powering mobile payments. When you hold your smartwatch or your phone near a point-of-sale terminal, you are bringing two highly complex devices into incredibly tight proximity, usually within like 4 centimeters.
And the physical limitation of that 4-centimeter range is actually a deliberate security feature.
Oh, interesting.
Because the induction field is so incredibly small, it is nearly impossible for a third party to intercept the transmission from across the room. The physical proximity serves as a verification of intent. You must physically place the device against the terminal to execute the cryptographic handshake required to process a payment.
That makes perfect sense. And the application of NFC that truly bridges all these technologies together is device provisioning.
Yes, that's a brilliant use case.
The notes detail how modern smart home devices, like a new wireless speaker, use a phone's NFC to seamlessly pass configuration parameters. Out of the box, a new speaker doesn't know your Wi-Fi password, and it obviously has no keyboard to type it in.
Right.
But if it has an NFC chip, you simply tap your phone against it.
You are utilizing the highly secure, physically constrained millimeter range of NFC to pass complex configuration data like the network SSID and the cryptographic keys.
It's just a perfect synthesis. You use the low-power, close-range induction field of NFC to execute the handshake, which allows the device to configure its internal radio, switch over to the 5 gigahertz Wi-Fi band, and begin pushing heavy audio data across the house using those 80 megahertz wide channels.
The technologies just seamlessly hand off to one another.
It's amazing.
You know, when you lay it out like that, the entire spectrum becomes visible. You start to see the physical architecture operating around you.
Yeah.
You understand that a dropped Wi-Fi signal isn't a random glitch. It's a measurable collision in a congested 2.4 gigahertz space. You see how Bluetooth survives on your desk by actively dodging those static Wi-Fi channels. And you understand the physical induction happening the moment you tap your watch to buy coffee.
It absolutely fundamentally changes how you interact with your environment. We've scaled from the massive wall-penetrating waves of the 802.01 Wi-Fi superhighways down to the localized 10-meter bubbles of ISM band Bluetooth devices, and finally down to the microscopic power-harvesting coils of passive RFID and NFC.
And armed with this knowledge, you really can see the matrix of your daily life. The certification notes focus on managing this from an IT standpoint, obviously, but the reality is that we are all network administrators of our own personal airspace. Recognizing why these technologies had to be designed differently empowers you to actually understand that space.
Absolutely. Now, as we wrap up this deep dive, I want to leave you with a final thought to ponder based on the source material we covered today.
Right.
We are already walking around with mobile phones that possess the processing power to generate induction fields and read passive microchips instantaneously via radio waves.
Right.
As these batteryless RFID and NFC tags get cheaper and smaller, shrinking down to the size of a grain of sand or becoming woven directly into the fabric of clothing, What does the future look like?
That's a huge question.
Right. Imagine a near future where virtually every physical object around us, from the clothes we wear to the products we buy, contains a dormant, batteryless inductor coil. What are the implications when those objects can secretly talk to the devices in our pockets, harvesting power to broadcast their presence the moment we brush past them?
It really makes you think.
The wireless infrastructure we've discussed today isn't just about connecting computers, it is rapidly becoming the nervous system of the physical world itself. So look around your space right now. The signals are completely invisible, but they are absolutely real.